Two chains. Sorry to make up for missing that outro yesterday. Welcome back. Last day before test day. I had a request to look at the last 2 pages of the test. So I'm going to take a look at those today, what we need to do to get ready for those problems. Again, the whole key is on Schoology, so check that out and try and figure it out if I didn't specifically address the question in today's video or yesterday's video. So let's take a look at the second to last page in the book, or in the review sheet. So we have here a graph in front of us. I can tell by the y-axis that this is a velocity and time graph. So it says the graph above shows the graph of v of t, the velocity in feet per second on the interval 0 to 12 seconds for a student biking to school. This is a no calculator problem. Okay, so we're looking at a velocity time graph, and when we take a look at the questions here, we just have to keep in mind that this is a velocity graph. Sometimes it's a good idea, just so you don't forget, just write the word velocity up here. So every time we look at that graph, we don't forget that that's a velocity graph. The first question says, what is the velocity at t equals 6 seconds? Include units. This is a very simple question because it's asked about the velocity at 6, and we have a graph that tells us the velocity at all the times between 0 and 12. So taking a look at our graph here, when time is 6, our velocity up here is at 0.3. So we know that v of 6 equals 0.3. And then we need the unit in here. It says right here that velocity is given in feet per second. This is a velocity. So we get that pretty simply. The one thing that caught my attention there is that the graph here, my t-axis counts up by 1 each time. My velocity, though, only counts up by 0.1 each time. Interesting. Okay, so that just to keep that in mind when we have to find slopes eventually, that's a real thing. Next, B says, on what intervals is the student traveling to the right? So when we take a look at this, we see we need to know, first off, by definition, traveling to the right. What good students need to know here is, or what everyone needs to know, because you're all good students, what we need to know here is that traveling to the right means velocity is positive. Right away in our mind, when we read that question, I'm interpreting this as, where is v of t positive? Okay? And again, I have a v of t graph. So I want to know, where is this graph right here? Where is this graph, for what t values, is the velocity positive? Well, I noticed, and what I know here is that velocity is positive anytime my velocity graph is above the t-axis. Okay? I don't care about slope here. I just care about what times this graph is above the t-axis. Right? Here's the t-axis. Anytime we're above that line, the velocity is positive. Okay? So I want to report all the positive velocities. So by looking at this, I can see it's going to be from 0 to 2, union 5 to 12 seconds. I need to justify. Well, my justification is what I did in my head to choose that correct interval, because this is where v of t is positive. So those times our velocity is positive. If the question would have said on what intervals is the student traveling to the left, I would have reported 2 to 4 as my answer, because that's where velocity was negative. C says, the student was biking to school and realized she forgot her calculator at home. At what time did she turn around to go home? Okay, turn around is another way to say change direction, right? Notice it says what time, not on what intervals, or during what interval, or what are all the times, right? This is looking for one specific time where she turned around, where she changed directions. Well, changing directions, again, what we have to know, changing directions means that velocity switches signs. So I'm looking for when does v of t change signs at the beginning of our graph here. Well, v of t changes signs right here, because that's where v of t switches from positive to negative. So we would say at t equals 2. At t equals 2, we need to explain because that's where v of t changes signs. Okay. So turning around is the same as changing direction. D says, what is the acceleration at t equals 11.5 seconds? Okay, so the first three questions here, A, B, and C, all had to do with velocity, right? I wanted to know the velocity in A. I wanted to know when we were going to the right. That's a velocity question because it's where velocity is positive. I had a turnaround question. That's where v of t changes signs. This question is now about acceleration, so we need to be careful when we address this problem. The first thing we want to do is figure out where t equals 11.5 seconds is, right? So we're talking about this part of the graph right here. Right? I know the velocity at 11.5 appears to be 0.1, but I didn't want the velocity, I want the acceleration. Well, how do you go from velocity to acceleration, you might ask? Well, that's very simple, something we definitely need to know. We do the derivative. So we don't have a function to do the derivative of, so we think about the meaning of the derivative. Derivative is the slope of the tangent line. Well, this is just a line segment here, so I want the slope of that line segment. So when I look at it, whenever I calculate slope on a graph, I just look at rise over run. Our rise here is we drop 2 blocks. Remember, the blocks are all 0.1 here. So I drop 0.2 and I run 1. So I get negative 0.2 over 1. So I get negative 0.2. And this is acceleration now. So I'm going to be in feet per second squared. Again, this equals A of 11.5. Okay, so we had to do the derivative. Oh, we don't have a function to do the derivative. Think about what derivative means. It means slope. Good. Part E was cut off on my screenshot here, but I asked you at t equals 3.5, is she speeding up or slowing down? To answer that question, again, anytime I ask about speed increasing or speed decreasing, or speeding up or slowing down, what we need to immediately go to is I need to know v of 3.5 and a of 3.5. So right away before I guess, oh, it's increasing or decreasing or speeding up, slowing down, whatever. I don't want to guess this. I want to get an I want to figure out what v of 3.5 is, and I want to figure out what a of 3.5 is. I need to check both or I can't get this problem right. Okay, so v of 3.5. That'll be easier because I have a velocity graph. I'm going to locate 3.5. It's right there. My velocity at 3.5 is negative 0.1. And most importantly, I know that v of 3.5 is less than 0. Okay? A of 3.5, right? We learned from part D that we calculate the acceleration by looking at the slope of our velocity graph. When I look at the slope of this graph, I see that this slope right here is positive, right? If I wanted an exact number, I'd go up 0.2 over 1, so I'd have a slope of 0.2. But more importantly here, I know that A of 3.5 is positive. So now I can answer the question. The student is slowing down at t equals 3.5 because, again, what was I looking at? Well, I was looking at the sign here. This sign is negative, this sign is positive. The signs are different. So I have to say that, but I want to specifically say the velocity and acceleration signs are different. So I'm going to say because v of 3.5 and a of 3.5 are different signs. Okay. So hopefully that helps us attack that problem. All right, I want to fast forward to the back page. We haven't done a lot of table work specifically with this standard, but we have done table work before, and just know that on AP tests, tables show up a lot in a lot of different contexts. So when I look at this table here, I notice I'm going to notice these two boxes first, where my x normally goes is t seconds, right? And in my y box, I have x of t meters. Right? I know right away that x of t is a position function and t is time. So this is a position time table. It says the table above gives selected positions of a particle moving along the x-axis. X of t is measured in meters and t is measured in seconds. Okay, so I see units, right? It's always a good idea to underline those. So when we have to give units, we can give the correct ones. It says estimate the velocity of the particle at t equals 10 seconds. So what we have to know here is that velocity, how do we get to velocity from position? Well, we do a derivative, right? So I want to estimate the velocity at 10. Really what I'm doing here is I'm estimating x prime of 10. Well, we know how to do estimations of derivatives from our very first unit. So when I take a look here, 10 is in between these two spots on my table. So I'm going to say v of 10. That is going to be equal to x prime of 10, right? So I'm estimating a derivative here. You don't have to have both of these here. You could just have either one. But we do need a wiggly equal sign here. So that approximate derivative here is going to be, right? It's going to be x of 12 minus x of 8 over 12 minus 8. Okay. Or you could have 10 minus 22 over 4. 10 minus 22 is negative 12. Negative 12 over 4 is negative 3. Our unit for velocity here will be meters per second. So our best guess of our velocity at t equals 10 is going to be negative 3 meters per second. B says, what is the average velocity on the interval 0 to 16 seconds, right? This is another way of saying velocity is the rate of change of position. So this is another way of saying average rate of change. So we can say average velocity on 0 to 16, right? We can use just a regular equal sign here. That equals the x of 16 minus x of 0 over 16 minus 0. Right? X of 16 is 2 minus negative 6. I'll write that as 2 plus 6 over 16, which equals 8 over 16, which equals 1/2. Again, it's talking about a velocity here, so it's still in meters per second. So our average velocity over the whole thing was equal to 0.5 meters per second. And that's not an estimation, that is our actual average velocity. Okay, let's take a look at the next table. The first thing I notice about the next table is now this is a velocity time table. Okay, different than the one before. So number 9 says the table above gives selected velocities of an object moving along the x-axis. V of t is a continuous function. Okay, that's important. The other thing I want to notice here is that there were no units given in this problem. So my answer is, yay, I don't have to worry about units, which is nice. A says, estimate the acceleration of the object at t equals 9. So we have information on velocity. We're asked about acceleration. This is obviously going to be a derivative, right? A of 9 always is going to equal the derivative of velocity at 9. And we're estimating here again, so this is just like part A on question 8. However, we're going from velocity to acceleration instead of position to velocity. So A of 9 or V prime of 9 is approximately going to be V of 12 minus V of 6 over 12 minus 6. Right? It's always these ones divided by these ones. Right? V of 12 is 18. V of 6 is 2. 12 minus 6 is 6. 18 minus 2 is 16. 16 over 6 reduces to 8/3. No unit needed here. If there were units in this problem, I'd want to make sure that it's an acceleration unit. So it'd be a distance divided by a time squared. Okay? Part B says, explain why the must, that's a typo by me, explain why there must be a time c, where 0 is less than c is less than 6, where v of c is equal to 0. Okay? What theorem am I going after here? IVT, right? Hitting a certain velocity when I know a starting velocity and an ending velocity on that interval, right? I know v of 0, I know v of 6. I know that v of 0 is less than 0. I know that v of 6 is greater than 0. So I have to hit 0 somewhere in the middle there, as long as my function is continuous, which it says it is in the information at the beginning of the problem. So dust off your old IVT brain to figure this one out. Here's what we need to say. I'm looking for certain things here. First thing I like to do is state the condition necessary. Condition necessary is continuity. So I'm going to say since v of t is continuous, so I need to state continuity. I want to state the surrounding values. And v of 0 equals negative 14. And v of 6 equals 2. There must be a time c. Now I can just kind of restate the question prompt. There must be a c where 0 is less than c is less than 6, such that v of c equals 0 because of the IVT. So again, when I grade this, right, if I was grading this, a student's work on this, I would make a check mark on continuity. The student must state continuity if you're going to use IVT. I would give a check mark for my surrounding values. And then I would give a check mark for invoking the IVT. Okay? All those things are important. All right, there was a question C that cut off. But it was, what is the minimum number of times the object changed directions. Okay. Again, asking about changing directions, I know that velocity has to switch signs. Now, this could have switched signs, velocity could have switched signs 1,000 times in this interval, right? Because that's the thing about tables. You're really limited on what you know. However, there are some things that we can guarantee as long as this function is continuous. So take a look back at the table, and let's say, where can we know for sure that we had to change signs? Well, take a look here. My velocity at 0 is negative. My velocity at 6 is positive. Because the function's continuous, I know I have to go through 0 and I have to switch signs somewhere on that interval. It might be more than once, but it has to be at least one time. So there's one place where I had to have changed directions. To go from 2 to 18, I do not have to change directions at all. I could have, but it's not a guarantee. So I can't find one there. Going from 8 to 15, again, velocity did not have to change signs to go from 8 to 15, or sorry, 18 to 5. However, on this last one, switching from 5 to 8, there's another time when I must have gone through 0 and switched signs. So there are 2 times. So there are 2 times when I must have changed directions. Okay. There are 2 times when I must have changed directions, and I know that because there are 2 times where my interval switches signs. Okay? You can say this occurred on the interval 0, 6. So there was for sure a direction change on 0, 6, and there was for sure a direction change on 18, 24. There may have been more than 2, but I know for sure there are at least 2. That's it for today. Again, study hard, look this thing over, make sure we're ready to go tomorrow to dominate this thing. See you guys tomorrow. See ya. 2 chains. I didn't forget this time. Bye.